Okay, so here we are. Today we are going to discuss and see how the journey from kernel to OS happens. Last time or some time back, we actually saw that the kernel is nothing but a simple one single program with very little of a size compared to what the total of the OS takes of the disk. So in my system, I have two kernels installed. One is the Linux and the latest Linux, and the another is the LTS version of the Linux. So and both of them are around 17 to 16 MB, less than 20 MB you can take. Of course, there are other modules or the drivers which Linux loads as and when is required. But today we are going to understand and see how the whole process takes place. So here I'm typing this command ps3, which shows you all the processes that are currently running in the system, but in a different way. I mean, it shows who is the parent of which process and everything. So it basically says systemd is the parent of all these process: bluetoothd, crash helper, dbus broker, launcher, ewu, and iwd. All these processes are actually at some point started by systemd, and then you can see the login process actually starts a process called start hyperlane, which in turn starts the hyperlane, which in turn is starting the Firefox, and this terminal, and WL frame, which is my wallpaper utility, and whatever it basically. And OBS is also being started by systemd. OBS is recording my screen and voice right now. There is also another copy of systemd and all this. Now, generally, we don't have to think about all of this because it's managed by systemd, which is arguably the most popular of the service manager of this thing. But today we are going to dissect what this is doing, systemd is doing, and we are actually going to take a kernel and take up the responsibility of systemd and do these things ourselves. Sounds fun? Let's dive right in. So the let me show you something. If I pass in -g to the ps3 as a parameter, then it shows the same thing, but there is a slight difference. Now it shows the numbers in parentheses for each of the process names. These numbers actually correspond to the process name, process ID, and as you can see, system D has the process ID of 1, and this is interesting because the process IDs are given incrementally. So we all know that all the services and programs ultimately has to be started by the kernel. You can ask kernel to start a process, but it is the kernel which is actually starting the process, because it is managing, last we also discussed, right? This is the kernel manages the hardware as well as it manages the processes. So the kernel starts the process and it gives the numbering in an incremental order. The first process is always given the ID 1. So as you can see, systemd holds the process ID 1, which means this was the first process. And then you can see there is nothing which is at the same level as this one. If I zoom out a bit, maybe it be difficult to see, but maybe I can guess. So this one, if you see, everything is a child of this process, the systemd process. Let's zoom in a bit because this might be difficult to see. Yes, so systemd, the first user process, is actually the first process started by Linux, and also this is the only process which is started directly by Linux. I mean, without any process asking to be started. So all the other processes are started by Linux because some process asks the kernel to start it. But this is the only process which the kernel started by itself. It is called the init process or the initializing process, and this is the first thing that runs after kernel loads up. So the process starts as kernel boots up, it then it goes to sets up the sets up what you can say sets up takes up the system, you can say takes control of the systems, then sets up necessary interfaces. We discussed last time, right? There are many interfaces which the kernel exposes. For example, there is lsys, which exposes the device tree in a sense. So all the devices and all the virtual and physical devices connected to the system are represented through sys. It's a different file system. Then there is dev, which is also contains the devices, and the proc also, which shows a representation of the running processes. All this interface, and there are also other interfaces like syscalls or ioctls and interrupt handlers, which needs to be handled by the kernel. All those things it sets up, and after it sets up, it basically after that it starts up. It starts the init process with PID equal to 1 basically. It starts the init process, and then after that it is the in a way it's a responsibility of this one process, the first process, to actually start up all the other services, including your display driver, including your display server like Wayland or X11, your audio server like Pipewire or Pulse Audio, your session manager like SDDM, GDM, or no, if you are running a proper desktop environment, the whole service chain has to be started eventually by this one process called init process PID1. Now this is well and good to see and to know what's the process like, but it would be much cool if we can see this in action, right? So this is why I have set up a virtual machine where I have compiled the Linux kernel and set up the minimal system that we can play with. So we will basically we will come in we start a shell process. We'll come in at the point where it is going to start the init process, and we will instead of systemd, we will provide the kernel with a specific program to run, a shell, basically a shell program to run, and then basically we'd see how the system is at that point of time. So kernel boots up, takes control of the system hardware. It should be system hardware, not systems. Takes control of the system hardware. All this sets up the necessary interfaces, including syscall, virtual file systems like sys /proc. Then it all the other interfaces like interrupt handlers, the syscall handlers, ioctls, everything that is required, and obviously also the other processes like scheduling process and the CPU management, time management process, CPU scheduling, memory scheduling. So this scheduling process, every internal feature is of the kernel is started up, everything gets ready, and once the kernel is ready, it starts the process, the init process. Now what we will do is we will instead, generally in our system, as we saw with this command, systemd is the first command that is being run by the kernel, and you can also view it in here. Let's see for all users, and if we just the tree view, you can basically see the PID1 is systemd, and if we press C, we can actually see the command which was actually run. So this is the process, and it was actually run with these commands. And this is the first process, that the kernel. Every process is a child, direct or indirect child of this systemd or the init process. Maybe you are familiar with htop interface. You see much things here like this one, and this is it. So now, before we dive into our minimal Linux system, I'm going to show this part. I have added a banner like this one. So as you can know, my system is named DevStation. When you are seeing DevStation here, it means we are in my system, and when you see rxrjlinux, it means we are the minimal system. Obviously, I have not yet started this system. So currently we are still at DevStation, our host machine. But once we start this Linux system, it's a virtual machine. We are running a virtual machine, and basically virtual machine, and the output would be shown here for simplicity. Actually, let me just show you what actually happens. QEMU system x86 64, and we pass in the kernel. I have already compiled the kernel. This is the compiled kernel, bjad image. It's 15. This is the kernel, bjad image. And obviously, when the kernel starts, it needs to have a file system, right? A place where to call /ls/, and this is a proper file system. But Linux needs a file system to start, and we are providing a simple enough file system with just one binary and one simple module. But yeah, so we need to system x64. We say kernel as bjad image, and then we say init rd, which is the initial RAM disk, and we have to. This is a compiled version of compressed version of the file system. We are directly providing it to the kernel. If you don't understand all of this, just stay with me. We don't need to as of now. Just know the fact that we are starting in a minimal kernel without any system or any other program, as you will see. And if I start this, sorry, and we also need to say which UI 0. Okay, root equal to, okay, this is not good. This is not good. Run.sh. I forget this commands actually. Not console equal to t by 0. This is good. Actually, we can do this as well. Append console equal to t by 0. We can basically see this one itself. Console equal to tt by 1, and it starts the VNC server instead of root equal to RAM 0 maybe. Okay, I will start with this one itself. So TTY as 0, which means we are going to run the serial input and graphic. If we run this program, now we are inside the kernel, and this is now you can see basically if we run ls, there is ls command is not found, nothing is present here. If we say type in system ctl, nothing is made. We type anything, basically it doesn't. There's nothing in the system. Obviously, it's not completely empty. We can use the tab completion to find what is available. There is an init file, which is the systemd in our system. So we are starting. This is the process that is getting started. Forget about setup.sh for now. We are going to do this manually. And dev is, you can see what the dev contains. As you can see, there is nothing inside dev apart from console. Console is basically maintaining the std in and std out, so that at least there can be some input and output to the system. And obviously, and there is user. If we see user and there is bin and lib, if we say check bin, we have only two programs. One is busybox and another one is ash. It's a shell actually. It's precursor to bash. It's a acorn shell. I think it's a implementation of acorn shell. Then busybox, we have chosen busybox because busybox provides us all the utilities. For example, busybox, if you want the ls, we can type in ls and it will show us what the current system has. So as you can see, and obviously if we type in ls-l, we can actually see that all that we have in this system, the root directory is a dev directory, which obviously contains only a console file, console device. Then there is a root directory, root directory, which is empty. Then there is user, which contains bin, lib, and bin contains the busybox, ash, and the lib contains obviously there's modules. I'm going to show you how an example of how to load, how the kernel loads up a module, a driver module. I've chosen a specific case for this, but for now, let's say box. I am going to power up the system. Why? Because there is another thing that we need to check. We need to provide a, actually, let's start with this one actually. What happens is if we basically forgot this part of the file, we are basically adding a hard drive to the system as well, because we need a hard drive. We'd eventually need a hard drive. So we run this command, everything is done, and it's user bin busybox ls, and you can see it's still nothing is present, and ls user bin still has busybox and ash. Now with notice, now let's say this is rxrjlinux, we are in that minimal linux, and here we are dev station, we are at our system. Let's contrast this with this one. Like in our slash, we have all these different directories like proc, for example, the sys directory, the dev directory, the etc, home, and everything is present here. And but if we go again, we are back at rxrjlinux, and if we, of course, we don't have ls, but instead we have busybox, which can act as ls. And if we see what is present in the whole system, the slash directory, we see there is only these files present. Now let's contrast this. We saw at this point top, and we can see this is all the process running, or but how do we check the processes? Because we obviously we can, there is a process called top, but the top cannot display the processes because there is no proc slash proc. So as we last saw, the slash proc is an interface which a kernel provides as a view into the whole processes, and all the programs like top, htop, or anything are actually dependent on this interface. Top, htop, btop, whatever the process names, or even the ps. You might have heard ps is also a command. If you ps, if you see ps aux, and it will show you all the processes running in this system. We are currently at dev station here, that's why ps works. But here if we run ps aux, it will say okay, ps cannot open slash proc because no such file or directory. Now ls, we are at a completely blank system. Not completely blank actually, because the kernel has started, kernel is running, and kernel actually has the view of the processes, and it's already had set up all the hardware available to the system. But the thing is, kernel follows a style of kernel provides the mechanisms to do these things. So if you want to see the process, there is mechanism to do that, but kernel doesn't give you set up the system for you. Kernel the system setup has to be done by, it's actually responsible PID1, but PID1 can actually start another process which will do the thing. But essentially the kernel assumes that the whole responsibility would be taken by PID1, and it's up to PID1 what it does, whether it does by itself or not. Now the first thing we can do is we can mount the proc. So we say jar bin. Now busybox also provide a command called mount, which we can use to say, okay, we want to mount a file system of type proc. And what is the actual file system name? It's called proc. The kernel knows what's this about this thing, and we want to mount it at /proc. We want the /proc directory to contain to provide the window to this interface. So if we run this command, as expected, mounting on proc failed because no such file or directory, because we have to create the directory proc, and obviously we have to run user bin busybox mkdir. Every command that we want to run, we have to prefix this one, because every command is being fulfilled by busybox alone. And busybox mkdir /proc, if we do this, and now if we see ls, we'll see there is a directory called proc. Now if we do the mount part, we tell the kernel, we ask the kernel basically, we want the proc file system to be the file system named proc, which is of type proc again, and we want to mount it at /proc, this location. We want it to be placed here. So if we do this, no error generally, no output generally means success, and we can verify this with /proc. Now we can see the /proc has all this. It looks similar to our normal system, right? It has all the PIDs which correspond to individual processes. Then there are individual things like CMD line, then sys, then stat, or the mem info. If we see, where's mem info? Memory info. Okay, this shows the mem info. Then there is CPU info, obviously would be there, which would tell us what's the CPU uses in all of this. Now if we run busybox ps, since proc we have mounted proc, we can actually ask ps to see, okay, what's the view of the system, what are the processes running. And as you can see, /1 or the PID1, instead of systemd, we are running this process, which is actually the cell, this cell that we are basically seeing. This cell program is actually the PID1. It is the, and rest all of these are actually kernel processes. And the only process which is running on the system is the PID1, and this is us. We are running as PID1. We have all the responsibility and the power that the kernel provides. And obviously it also shows that we run the ps command, which we this one. Now obviously since proc is available, we can actually see run top, and we can basically see a real-time view of the system. As you can see, the user bin, the top is running with PID 72, and this shell is running with PID 1. And all the others are, you can see these brackets are actually signifying these are not user level processes. These are internal processes or feature threads that the kernel is maintaining. We cannot interact with these processes. Actually, we cannot directly interact with this process. For example, this one is a type of interrupt handler. Then this is kernel handling the dev file system. Then there'd be something, okay, let's forget about this one. If you see, the interesting thing for now at least is that we are running as PID1, and the if we see slash, we have proc as a file system. Now if we, and this is an interesting thing because kernel already has proc in its own RAM system, but it is not being visible unless it is not visible to us unless we explicitly ask the kernel to mount it at in a specified directory. Now we will do the same thing with sys. We create a directory called sys, and obviously we need to do /bin /bgbox mkdir /sys, and we have this thing sys that is available. Now what we do is we'll say mount a file system which is of type sysfs. The name also is sysfs, and we want to mount it at sys/sys. And if we mount this thing and ls this, now we have all this available to us. The kernel, the class, if you remember, class has all this thing like dmi. This was, if you remember, the motherboard info, right? Let's now see what is present here. So we can say there's not much BIOS. We can basically see the BIOS vendor, and instead of ls, we can say cat plus dmi id BIOS vendor, and we just see BIOS, and obviously this is not a real system. It's a virtual machine managed by the KVMU. So that's why there is not much information, but there are some information available. We can basically if you see the chassis per vendor says QEMU because this is not a real machine. It's a QEMU based virtual machine. Obviously, there's everything is available here. And if we see net, there is only loopback because we have not set up networking yet. And now ls. Now we are the way BGBox works is we have to type in the command to BGBox first, and then actually you can maybe type in BGBox ls also. It still works. There's no need to write the whole path because it's in user bin. The shell can actually find it. But and yeah, so the another file system, if we go to our system and if we see, there is also another system called dev, which contains all the devices. Dev, and you will see it contains all the TTY devices, the dev 0, the device which always gives you random numbers. Then there's the camera webcam devices, the device which always gives you 0, which these are virtual devices which are used at many places actually. And there is SCD in, SCD out, which are basically this is how the kernel gives you the std in as 0, std out at file descriptor number 1, std error at 2, and obviously there are the hard disk, the NVMe SSDs, all these which are present. But in our system there is, if we see ls dev, there is only console because we need to mount it. BGBox mount, the type of dev is actually dev tmpfs. Now if you are wondering how I'm getting these types, we can actually see df-h. You'd see the /dev is mounted on /dev. The file system is dev tempfs. You'd not see sys, but to see /sys and /proc, you'd have to type in a, which stands for all. Now you can see sysfs is mounted at sys. Then there is a /proc. The proc is mounted as /proc. There is a temporary fs. Temporary file systems are mounted at run. There is another temporary file system which is mounted as /tmp, and there are many other processes as well. So now we are back at our rxrjlinux and we are going to mount the empfs and slash. We already have the directory. We don't need to create another directory. If we mount this thing now, bgbox ls/dev, we can see we also have all these devices. For example, 0. Then there is all the TTY devices, the random devices, the devices which returns random numbers. Then the CPU, console, and everything is there. This is now a basic thing what we can basically run. Now, BusyBox interestingly also provides an implementation of VI. It's a simple editor. It's precursor to Vim. If you use something like NeoVim is a fork of Vim. Vim is based on VI, which is again based on ED and all of this, but we'll not go into that. But BusyBox provides a subset of VI. So we can actually open up a file. For example, let's see what the init process, this is what is actually the kernel is running. So we can actually see what is actually written here. As you can see, it's a pretty simple init script because we are not doing anything. We are just this line. It's just the shebang tells this is called shebang. It's hash or pound sign followed by exclamation mark. This tells you what is the program that should be used to execute this file, and we are asking it to execute this file with the shell, and we are running this command exec, which means execute the shell itself. So we are asking the shell to execute the shell, which basically gives us this this is what we start up. And obviously, if we do set up the message, it's a simple script that I have created. This is some things new because we want to do these things regularly, so we can basically have these things already created in a script, and then we can load this script as well. And obviously, these are basic quality of life improvement that we can do. This is well and good. Now BusyBox ls/ we are still almost at a 0 level system, but we can actually set up. For example, the kernel already provides the permissions. This is permissions are set up wrongly, but because we have set up the initial root file system wrongly. But if we want, we can actually change. Okay, let's say we change. Because before let's say BusyBox who am I, actually returns you the user of which is the current user. Now if it says who am I is unknown UID 0, which means the process has an ID, or the user has an ID of 0, but there is no name attached to it. So basically we are at a point where even the user root is not called root yet. So there is no name for the root. It's identified by the user ID. So everything works, the permission works. You have all the root privileges as you know it, but the user itself is not called root because you have to create the name actually. And for example, BusyBox mkdir/etc, the usernames actually comes from etc. And now if we say BusyBox vi etc pass wd, it actually holds the username of the usernames and password. The syntax is somehow like this: the username followed by colon, then followed by user ID, followed by group ID, then followed by a name. Sorry, we forgot one thing. There is a password, which is it's generally X, because the password is not stored here. It's stored in another file called /shadow, not in password, but originally this is where the password was stored. And for the record, we can actually we are going to store the password here as well. Then this is another identifier. I don't know what that really is. Then this is the home directory where the home of this user is. And then what is the shell, the login shell required for this, which is present for this user, bin ash. Now we need to go here. Not all vim commands are available here, but most of them are. Root x. Now if we write and quit this file, now if we say bg box who am I, it says root, because now we have given the a name to the user. Similarly, if we say cat proc sys kernel hostname, sorry, we have to prefix this with bg box. It says it has the default system name rxrjlinux, which I have set up while compiling the kernel, but obviously it's not rxrjlinux. It was because I took the config from my own system, so that's why this name is actually present here as well. But obviously we can change it to anything, and obviously now we can basically work our way and set up anything we actually want. But the interesting thing is, this is well and good, but this whole file system, if you see pg box file system mounts, I think it's called mount. It shows you all the mounts that are available. So you can see the proc file system is mounted on /proc, sysfs is on /sys, dev temp fs is on /dev, and there is a root fs on slash. It is not, this file system is not, anything that we change here is going to be wiped out, because this is not present in any disk. It is the whole file system is actually maintained by Linux in RAM itself. But what if you want to load a disk? Remember, when we started the terminal, the virtual machine, we attached the virtual disk to the system. In your real system, this is, by the way, this kernel can be run on your actual machine also. I am just showing it in QEMU because it is easier to record the screen like this, with in high quality. Actually, basically you can still record it with a camera, but this is basically much higher quality to show you. But since I have created a virtual disk to show you, but it is, if we see, there is bgbox/dev, bgbox ls/dev, and you see there is no SDA or something which generally shows us which our hard disk, or there is no NVMe, something like NVMe. There is nothing like NVMe. For example, in our, coming back to this dev station, if we say ls/dev, we can see there are disks like NVMe. This NVMe 0 is the character device, but this is the disk, the block device. Then these are all the partitions that are available on my system. But in rxrjlinux, there is nothing like that, because I have specifically made it so that you have to sorry about that, you have to load the driver first to be able to get to the disk. So for that, we have this command called bgbox mod probe, and we can basically say, actually, let me show you where the module is. bgbox/user/lib and modules. This is the release, kernel release. Actually, we can actually verify with bgbox cat/proc sys kernel os release, and we can see this is the version of the kernel that is we are running. And this Although we can ask the kernel to load a module, by default it will look in this directory. We have to provide the module from this directory itself. So we can say, okay, bg box user lib modules. So we have only one kernel running on the system, and we have to set this up, and there are all this file. I have set up a minimal system, but so there only one driver, which is vrtio underscore blk.ko. This is I think this is wrapping up because there is a hard limit on the number of columns that is available on this tty, but this should be a single file. In your actual system, this would be different. For example, in my system, ls user lib modules. As you know, I have two kernels installed, and each of them has its own set of modules. This is the latest kernel, and if you see, this has all the different files. These files actually tells what are the kernel available. And for example, if I see drivers, there are 108 directories of different driver. For example, this one contains the driver for NVMe, the SSD basically, then there is soundware, then the thermal drivers, all of this, the hardware monitoring drivers, the GPU drivers. For example, GPU, if you see, there's GRM, and we have all this AMD display drivers. Then there's i9-N5, which is Intel driver, Novu, which is the open source Linux driver. There are many different drivers available, and there is also a vrtio, obviously, drivers, block, block. Oh, okay. So I'm looking at this one. In rxrjlinux, I have placed this vrtio block, which is basically a virtual block device driver, which helps the kernel understand the QEMU virtual disk. So when we load this disk or load this driver, we can basically interact with the disk. Now, before we run this, let me just show you another thing again. If you see this, it contains all these things. Then this TTY, then there's then there's VCS, VCS1. All of these are present, but there is no SDA or something like this, something like that one. But now, if we mount this, load this driver, which is basically mod probe, which basically says probe the module, which basically means to load the module. And we don't have to provide the path, because mod probe will basically find out the path based on the currently running kernel, and we just need to provide the driver name, which is vrtio blk, which is virtio block. And if we run this thing, cannot change directory to /lib modules. It is no file in direct or such file or directory. It is showing an error because it is trying to find the modules in /lib modules. But if you remember, in our system, we have it in /users lib modules. This is and because we don't have a lib folder in the root system, and this is easily solvable with, we can basically say, because we don't want to keep separate modules, we can say ln, which is basically create a symbolic link, s for symbolic link, and then we say create a symbolic link to usr/lib and place it at /lib. Now, if we say ls/, we have a symbolic link called this one. If we lib is actually pointing to user lib, so lib modules will actually points to user/user/lib/modules. Now it is actually reachable. It should be reachable. Now, if we load the module again, mod or probe the module, which basically loads the module, virtio block, and if we load this, nothing is shown in output, which generally means everything went on okay. We can actually now bg box ls/dev Now you can see everything is still same, but there is this one. This is a new one which came up, VDA. So it's a virtual disk, so that's why it's called a VDA. If you add another more disk, it will come up as VDB, VDC, and all of this. If it had been a actual USB stick or something, then it would have come up as SDA, or no, a hard disk come up as SDA, and VME disk comes up as different name. Now, since we have VDA here, we can actually mount it. But before we mount, we can say bgbox mount the /dev VDA to this directory mnt. It's a convention to mount the directory drives in /mnt. But before we do this, we need to create the directory mkdir/mnt, which means bgbox mkdir/mnt. We do this and uncomment this line and run this again. Now we have a /mnt directory, bgbox ls-l / and if we clear the screen and run this again, we can see there is a mnt directory. And if we go inside mnt, this is a interestingly, this looks like a Linux system, because I have gone through the effort of setting up a basic system here. It already contains home directory, etc, the proc, root, this user and var, and everything is, all the symbolic links are already there. And bin, obviously, lsmnt/bin, which corresponds to user bin. It contains obviously two fields only, bgbox and the ash. AS is actually is a link to bgbox itself. So the shell is actually a link, symbolic link to bgbox. And obviously there are more. I have placed some things more, like for example lib modules. I have placed more modules here, as you can see. But in, or you can say etc. If we see etc, I have set up the host name, the init script, a different init script here. Then there's a password file, and you can see basically, if we see init. Now if we, let's see what the init actually does. Now that we understand the init script, let's see what's the init script at this the virtual disk. This is the whole contents of the virtual disk, what it actually contains. If we see, this is a bit more of a I have set up some things more. For example, this is basically log function. Then it's doing the same things that we just did, but in a more systematic way. In a sense, they are grouped together, and these are already present in init, so it will be done automatically when this is actually loaded by Linux. And we are actually storing the host name here, and as you can see, we are outputting the contents of host name and writing it to /proc/sys/kernel/hostname, which basically says the host name of the system. Then we are running some tty, this getty process, which actually helps us with the login process. You will see what this happening. Now we can, all and good, we can see, but we cannot run this init process directly, because we already have a / and this init process actually is going to look for things in its own system. So what we have to do is, we'll say, okay, everything is set up. We have the hard disk or the disk available at mnt, and we have loaded the devices. As you can see, ls/dev, we have loaded all the devices, even loaded all the drivers. Obviously, in an actual system, there'll be more drivers which should be loaded, like graphics drivers, sound drivers, or Wi-Fi drivers, Ethernet drivers. Many more drivers would be loaded up, but the idea is still the same. We basically do mod probe. This is the same idea. Obviously, mod probe and then the driver name. There are individual services. For example, it's coming back to dev station. If we see it in htop, we can see there are services like udfd, which is actually responsible for the handling the device drivers as you plug in devices, in real time. When you plug in a USB, a USB interface or some specific device at a particular USB, the UDFD looks, the kernel notifies UDFD. Actually, let's show you how this, now that we have this thing, we'll show you how this actually happens. But this is what we did to load the var block drivers. Now we can say, okay, we execute this thing, which is user bin bgbox, and then switch root, which, as you might have already guessed, we are going to switch into the new system. This is not going to stop the kernel because kernel is already running and it cannot stop and restart itself. The kernel is running. We are going to switch the root file system so that everything is going to change. And the first switch root, where we are going to switch, where the new root is, the new root is at /mnt. And what's the first program that we want to start? That's /init. This init is the init inside mnt, so it switches into this system and starts init process. And after that, the current root system would be gone, it will be deleted, and it's already only in RAM, so it be wiped out from RAM, and this would become the new file system, new root file system. Now if we do this, these are old logs, it's not being cleared, but as you can see, this now shows a login prompt and it already has a system name and everything. Now we can basically say root and we given a password. I have already set up the password, and if we log in, now we are at, as you can see, the prompts are already different. We can basically say pwd, it's already ls slash, it looks like a complete user system. Then we can basically say, okay, it's a top, and it basically say, okay, what's the root file PID one again? This is the new init that we are currently running. And the other process terminals are all different terminals are running. And obviously we can basically do, obviously that doesn't have anything. And once we are done, when we exit it, will not go back to your old system. Instead, the system is running on the new system is running on loop. It actually asks you to log in again. So let's say I log into, I have set up another user as well, it was, and I have set the password. This is it here. And now if we see pwd, it says this one, who am I, it was, and obviously ls, we see there is a file called hello.txt. Let's get this thing, and it says this is a working Linux OS, so you can interact it with like you do with the regular distribution. Currently only BusyBox is installed, but yes, you get the many different utilities, right? You can get all the cat is actually, if you see ls user bin cat, and if we see it here, it is basically a symlink. It's a link, as you can see, it's a symlink to BusyBox itself. In fact, if we see, all the programs are actually who am I, which, what, all these programs are actually symlinks to BusyBox itself. So there is in actuality in this system, there is only one program which is running, which is BusyBox. It provides all the functionality that in a for example, rmdir, reboot, for example, there is a reboot command also. All these are actually available. The formatting system, the IP, which allows us to connect to different things. And obviously this is a proper drive. Actually you can see this, as we saw, this has all the different lib modules, kernel drivers, GPU, DRM, then AMD. For example, this contains the AMD GPU. AMD GPU driver is present here. So if I load this Linux, this rxrjlinux in an actual system, not in a virtual machine, I can basically load this driver and I can get full access to this display as well. And there, the sounds and everything, it contains all the drivers and everything. If I so desire, I can actually run this as a normal system. The obvious pain point is that it doesn't have many programs installed. There is no package manager set up yet, so you have to compile everything, get everything yourself. But it is a proper Linux system nonetheless. It is an actual Linux OS. You may call it a distro, but it's a poorly maintained distro because it doesn't even have a package manager. But it is a distro nonetheless. Now let's take a look at a what is this? Let's take a look at Excalibur. Let me show you how things. Okay, sorry for the flashbang. Let me this. Okay. So at first point, the only thing that is started is the kernel, right? This is it. The kernel is the first thing that gets loaded up in the machine. This is the, let's say this is the whole machine. Let's say this is the whole machine. This is the whole machine. Let's say this is the whole machine. And kernel is the first thing that gets boots up. It loads, it basically, does all the things. For example, it sets up the system, sets up the kernel features, or you can basically let's forget about this one. Let's talk about this one directly. So kernel sets up all the features that is required. For example, it has to execute program, so it sets up the program execution, the CPU scheduler, the memory scheduler. It will need to handle IO, so it starts up the file system manager, the way it handles file systems and everything. And after everything is done, it sets up it also sets up the interfaces for connecting. So once interfaces, for example, let's say there are interfaces, these are, let's say, interfaces. This would include syscall, VFS, which is the virtual file system, and IOCTLs. Then there are sockets as well, like netlink and everything. These are set up. Then obviously it also, so interfaces are set up. Then it also sets up the CPU says that let's keep it a bit more high level and say process management features. Then obviously it also has to maintain the start the IO management features like disk IO and everything. All these things it sets up. All these things it sets this up, and then once it is done, once all of this is done, what it does is it loads the first process, or the PID one. The first process is given PID 1 and it is loaded. This is the first process, and now it has all the interfaces. It can, what did I do? Oh, sorry, I reloaded the system. It has all the interfaces at its disposal. It can, since process management is already started, it can ask new process to be created. It can do IO. Obviously, I'm right. These arrows are actually should be going through this one because actually, let me type it here itself directly. So something like this one. Did this one process management, and let's call it, instead of IO, let's call it hardware management features, let's say. So the through these interfaces, the PID one can access the process management feature, access the hardware features as well, and then it can basically spawn up all these different processes. Like for example, it can start, one thing is like, you, for example, in a real system, we did mod probe, right? Mod probe Bhart IO BLK. I don't like this font, maybe choose the different font. This one is good, this one. Okay, this one seems good. Okay. So we did this one, but it is cumbersome to do this manually every time, right? So there is a process, generally a process called udev. Udev process is called udev. It is run as a daemon, so it's called udev d there, but the essential process is udev. This is responsible for this basically udev. It also uses the interfaces, for example, the socket interface, for example. It uses netlink sockets, then the sysfs file system. It uses all of this to actually know when to do this, and when it finds a new device, it calls mod probe relevant module, the driver module, and basically loads the driver. So udev is actually responsible for, in your system, udev is the process which is actually listening, keeping in communicating with the kernel, because kernel is the one which will detect new hardware, right? So anytime a new hardware you plug in, kernel is going to detect, but it will not automatically start the driver. But since udev is communicating over the new netlink socket, it will basically know if there is a new device which is available. Then it will load. It might get the information here at netlink, but sometimes it might also get to scrape the sysfs file system to find the more information about the device, and then based on the device, it basically loads the necessary drivers. And once driver is available, it is available in /dev, which means all the other programs can now use that particular hardware. And similarly, there are other processes. For example, let's see. Let's see what are the processes which are running on my system to give you an idea. So as you can see, this is the UDFD. This is part of systemd. In systemd is providing the UDFD part. It is actually keeping track of all the drivers. Network D is basically maintaining the connection part, as is obvious from the name, and it's basically setting up which device or which connection needs to have which IP, which address, and how the routing should be handled, and all of this. Dbus broker is basically a communication channel between different processes. We'll go over dbus in a separate video out of the scope. Bluetooth of this video actually, so we go into more into dbus later in a later video. But for now, systemd network D, it manages network. Obviously in your system it might be different, because you might have network manager running which is handling the networks. I have systemd network D which is configuring the network, and IWD is for actually connecting to the Wi-Fi hotspot. This is can actually systemd network D can only assign IPs and manage the network. It does not have the capability to connect to a Wi-Fi hotspot, but this one does. This one connects the hotspot, sets up the initial networking interface, and then it configures the interface. If you are running something like network manager is the configuration part, and then you would see in place of the IWD, you would see something like WPA supplicant. That one is the process which is actually connecting with the means scanning the Wi-Fi card, finding Wi-Fi hotspots or access points and connecting to it, all of this. Then there's KeyD, which is it's a key mapping daemon that I have used. It's a key remapper basically. And systemd login D, it basically maintains a database of the currently logged in users. Login rituals is basically the process which is when I log into the system, the login process starts, which in turn starts all the user processes. So everything, most of the processes which are started from inside my user is actually present inside this. And but there are some processes like this four. These are actually, for example, systemd. This is also a systemd. This is also a systemd. But this has user/user, which means any processes which needs to be running with user privileges, not the system level. For example, this has a dbus. A dbus is a communication channel for different processes. This is a different communication channel for all the processes which are running in my user scope. For example, this pipeware pulse, these two are managing, allowing me to play audio. I mean, Linux is providing us the capability to play audio, but these two are managing that so that multiple applications can play audio at the same time. The mixing capabilities and everything. Decom service, there are different configuration service which helps us in keeping configurations. XGD desktop portal, these are portal which helps us, to, for example, this one, when you type in Control O, it open a file to do this. When I say Control S, it wants to, okay, this is not, but if you say Control S, it says where to save this file. These UIs are being handled by the portal. Obviously, the screen share also is handled by the portal. If you are running and there is OBS running, obviously, all of this is present inside login systemd, the user level systemd. Then there is Firefox running, Firefox Crash Helper. But if I go into login, I can see my window compositor is running, Hyperland is running here, and it running two terminals. One terminal is at running this first workspace. Then there is this is also another terminal which is managed from this one. You can actually see one is running bash run.sh, and here you can see basically the qm or is command is being running here. So yes, as we saw, udefd is for, these are all started by systemd, the PID one. This actually started this one. Then there is, it has to set up networking services. Then there is no any networking services. Then maybe what more you can do. There are other services as well, Bluetooth and Wi-Fi and everything. But essentially, this is the most essential part, because without drivers, you cannot use hardware. The drivers are already present. Linux is the one which is, when we call mod probe, Linux is the one which is loading the hardware. But as we saw, Linux or the kernel provides mechanisms to access the system. But user space, we call it user space because anything which is not running inside of kernel, and by inside of kernel I means anything which is running at a permission level, at a level of the kernel, which generally means the kernel, all the kernel features and the drivers. These are the only, kernel and the drivers are the only two things which are running at a privileged level of the kernel. They have full access to the hardware. Any program, including the PID1, including udev, including networking services, including your user session manager, which is basically saying how to let user log into the system. All of these are all part of user space. These are all part of user space. And these, type in a different color, maybe green. So it's green. Okay. This one is actually the kernel. It's called kernel space programs, basically, which means these programs are running at a privilege level that is only allowed for the kernel. It says this anything running inside kernel space basically has the full access to all the hardware, and anything running in user space, which includes the programs that are running with root privileges. Root privileges does not mean kernel space. Root privileges, any including PID1, the device manager. You can think of it as device manager. It's not actually device manager. It's basically real-time maintaining of the device and checking up devices and loading the necessary, asking the kernel to load the necessary drivers as required. Then there are networking services. These all are running in user space. And if you see, at least if you get these things correct, actually, even if networking is also a bit not essential for the OS, but no, it is to use like a normal system. You would need networking, but to be called the OS, which means you can use the hardware. You need the device drivers. You need some way to call mode probe, or you can manually call mode probe like we did. For example, this one, we are here, we are still logged in, and if you still at a login screen, we are basically inside rxrjlinux. We didn't have udev, we didn't have a user session manager, we didn't have networking services, but still we are inside a proper kernel, and we can log into the system. We can use the system, or whatever is present in this system, we can actually use it. Everything, including, for example, if you log, the permissions are all set up correctly. For example, exit. If I log into Rituraj, now if I say okay, vi, let's say etc pass wd, this has 2 users. Let's say I want to change the username or something. I change this password. Let's say I change this password. This is obviously encrypted. This is not the actual password. It's stored encrypted. And if I try to save it, it says etc password is read only, and we cannot actually write to this file because if we see ls-l, this file is allowed to be written to only by root. So everything is present. All the user level permissions are already set up. This is when we can access the hardware. We can obviously have not set up. There are drivers available on a real system. We can load the modules using mod probe. And for example, in a actual system, I can say, okay, AMD GPU, I want to load the AMD GPU drivers. Operation not permitted because I'm at not at Rituraj. If I go into root, then I can say mod prop AMD GPU. Could not allocate, obviously, because this virtual machine doesn't have, I think it's running on how much RAM, I think. RAM, what's the RAM? Memory. Okay, let's see. Free H. So there's total of 80, around 79 MB RAM is present in the system. The whole entire RAM and we are using 30 MB RAM with all these services and all, including Linux and everything. We are basically using only 30 MB of RAM. So obviously it's a pretty efficient system, but in the sense it doesn't have anything running, so it's on just the kernel. It doesn't take much RAM used, and but this is an actual system that even if we provide more RAM or if we load this system in actual hardware, we can use the system as we would normally. And if we download the programs and set up individual programs properly, which I may go and create another video for this on an actual system where I maybe create a video from rxrjlinux itself, right? That would be cool, right? Maybe I can I will go into that in a future video. but for now this is an actual Linux system. And we are talking about, I totally forgot this was what I was talking about. Linux kernel provides the mechanism to access the system. User space programs use those mechanisms to set up the OS. Basically, you can say set up the OS. It applies the policies and everything. So which user should be accessing which one. So if, for example, the init process can have one process, for user session manager can have there could be another process which handles the permissions required for each and every processes, each and every user, which user can access which one. All these things are ultimately provided, these functionalities are provided by the kernel itself, but the kernel doesn't do it by itself. It provides the mechanisms to do this, and it starts a single program, and then you can basically do all this yourself. You can ask the kernel to do all what you want and load up any hardware, use the hardware, start multiple programs, or like in our use case, we kept we never went on to more than 2 to 3 programs. But yes, so you can basically stay at a single program itself, or you can spin up multiple processes like a real system. Like, for example, this is 12,348. Obviously, this doesn't mean there are 12,348. There's 528 threads, 65 programs currently running on my system, 527 threads, 252 kernel threads. But everything, when kernel starts PID1, the first process, which is generally placed there, /sbin init. This is where it generally placed there. And if we see in this is a real, in my system, you can see sbin init, sbin system binary init actually points to user lib /lib /systemd. This is the executable. Actually, you can see lib systemd. This is it's a 64-bit executable. It's a executable program. This is the first systemd is the first program, which is also the service manager. It manages the services, starts up all the different services like UDEV, session manager, networking services, and Bluetooth and everything required. And then the user system manager lets us log into our user and actually use the system with our provided privileges. So that's it. Now you know how from kernel we get to the OS, which is basically, if we enclose this whole thing in this thing, this instead of machine, we can call this OS and it's here. So this is how the kernel kernel starts a program, and then overall they together become the OS you are actually using. Great. See you in the next one.